Hey everyone, Mr. Fransky here. Today we're going to be talking about the fundamental theorem of calculus, and that is, if there has ever been an intimidating title, I think that's the one. But it does have the word fun in it, so we're going to have to make fun, of course. And fundamental, of course, means that this is kind of the foundation of all of the rest of calculus, and we are going to be using this for the rest of the year. Kind of what this theorem will hinge, everything we do for the rest of the year will hinge on what we're going to learn in this lesson. So make sure you take careful notes, and let's kind of get into it. So some of the key vocabulary you'll be using, accumulation function is something new that we're going to be talking about. The tower of functions is something I've kind of mentioned in class a little bit. And then always average value, which is what we learned in the last lesson, will come into play in the proof. So let's get into it. So the first thing we're going to do is we're going to define kind of a new function in a new way that we haven't seen before. And what we're going to do is we're going to use an integral to actually define a function. So we have this function right here. And it looks like it's just a few different line segments, each with a slope of either -2 or +2. And what we're going to do is we're going to say capital F, this is kind of convention for fundamental theorem, capital F of x is equal to the integral, we're going to say from 0 to x of, let's call this guy here little f of x. So integral from 0 to x of little f of t dt. Okay. So what this means is that for any value of x, we're going to integrate from 0 to that value, and that's going to give us our big F function. So let's just think about finding some values here. Like if we wanted to find capital F of 1, well, just like every other function we've ever done, whatever x is, we put it in where the x belongs. So f of 1 is going to be the integral from 0 to 1 of little f of t dt. Now, you might be confused with why we're using t's. And remember that this is a dummy variable. It doesn't matter what this variable is in here. If we integrate it, it's going to be the same thing. We're just finding the area under the curve. The reason we can't use an x is because if we had an x here, we'd have too many x's, right? Because then f of 1 would be integral 0 to 1 of f of 1, but that would be a constant. So we have to use some kind of a different letter in here to be able to define it this way. So let's find this value. So the integral from 0 to 1 is just going to be the area of this triangle right here. So the area of that triangle is 1/2 base times height. So 1/2 times the base, which is 1, times the height, which is 2. So that gives me an area, or a function value, of 1. So there's a +1 area in there. Okay, so I have f of 1 is 1. Let's do f of 2. Well, f of 2, I think we can use some symmetry to figure that out, because it's going to be these two triangles added together, or this one big triangle. That's going to be another +1. So it looks like f of 2, it's integral from 0 to 2, f of t dt. That's going to be 2. Let's do f of 3. Well, f of 3, let's see, so we have +1. We know that integrals, when we have an area underneath the curve, that the integral value then is actually going to be negative between 2 and 3. So from 0 to 3, we have +1, one more +1, and then this guy right here is actually giving me a -1. So f of 3, if we do our integral from 0 to 3 of f of t dt, that's going to end up being back down to 1. So now some of the tougher values, what if we wanted to do like f of -1? We'll do f of -1, we'll also do f of -2. So f of -1, that would be the integral from 0 to -1 of f of t dt. And remember from our integral properties, we don't love to go from a right value to a left value. So what I'm going to do is I'm going to use our integral property that says this is the opposite of the integral from -1 to 0 of f of t dt. Now that's as if I was going forwards, which I like better. So we know the area underneath here. So the integral from -1 to 0, that would be -1. But because we're going backwards, it's the opposite of that. So this is -1, which is +1. So f of -1 is +1 because we're going backwards and the area is underneath. So I'm going to change that actually to, well, let's leave it as a negative. That's probably better. We know the area is 1, so because it's below the graph it's negative, but because we're going backwards it ends up being +1. And then f of -2, same kind of idea. We got another -1 here, but because we're going backwards, it's going to be the opposite of the integral from -2 to 0, f of t dt. So that's going to be negative, negative 2, which is positive 2. So now we kind of have an idea of just how to get these values, because this is kind of a weird defined function. But getting different values, we're just integrating from 0 to that value to get each of the function values. So now what we're going to do is we're actually going to plot some of these points and see what they look like. So here what we're going to do is we're going to plot capital F of x. So we're going to go back and forth a little bit. So remember, capital F of x, we call this an accumulation function because it's accumulating area from a point to whatever function value we want. So f of 1 is 1, so let's plot that. F of 1 is 1 right there. F of 2, I think, was 2. Yeah, that's what it looks like. And then f of 3 is 1. So f of 2 is 2. F of 3 is 1. F of negative 1, I think that was positive 1. Oop, too far. F of 3 is positive 1. F of negative 1 was positive 1. And f of negative 2 is positive 2. Let's think about f of 0. I'm going to do that one. Keep going the wrong way. F of 0 would be integral from 0 to 0 f of t dt. That was one of our integral properties. If we integrate from the same value to itself, that's always 0. So that means f of 0 is 0 right here. Now let's think about how we would connect this graph. Very rare that they ask you to make this graph, but I just kind of want to get a picture and talk about it. So between 0 and 1, this is not going to be a straight line. Because if you think about how we're actually accumulating area here, at the beginning we're accumulating area slowly, but then we end up accumulating faster and faster and faster because each one of these bars is going to get longer. So we have a curving graph coming from 0 to 1, kind of like that maybe. And now let's think about what happens between 1 and 2. Between 1 and 2, we're still accumulating positive area, but it's slowing down. We're still getting positive area, but it's slowing down because it's the opposite of what happened between 0 and 1. 0 and 1, we were getting longer lines. Now we're getting shorter and shorter and shorter lines. So it's going to be increasing still, but at a slower rate. So it's going to basically curve downwards like this. Looks like we might have an inflection point there at 1. And then between 2 and 3, what's going on is we're actually getting negative values. We're losing ground on f because we have these negative values going down. Okay, so what that means is going to go down like this. And on the left, it's pretty much the opposite. When we go left here, we are gaining more area. And because we're going right to left, even though it's below the graph, we have positive values. So that's going to be curved going upwards like this, something like that. And then if we continue going, we're going to actually be continuing to gain area, but it's going to be getting slower and slower and slower. So we're going to curve downwards like this. So now, what I want to think about is, okay, if this is what f of x looks like, let's think about what the derivative of that graph would look like. So the derivative of this graph, well, let's plot our zeros first. It looks like there's a horizontal tangent at 0 and at 2, so let's plot those. It also looks like we have a horizontal tangent happening at negative 2, even though it's right at the edge of the graph there. And then it looks like we have increasing concave up at the beginning. So that means that we're going to have a positive derivative that also has a positive slope. So we have positive derivative with positive slope. So maybe something like this. It kind of looks like a part of a parabola. So maybe like a straight line up to 1 there. Maybe something like that. It looks like, yeah, that slope could be maybe 2. I believe that. And then between 1 and 2, still positive derivative values, but we're concave down now, so we'll have a negative slope. So something like that maybe. And then between 2 and 3, we have decreasing, so it's going to be a negative derivative, and it's concave down, so it'll also still be sloped down. So it looks like that line kind of just continues. And then on the left side, right here we have decreasing graph, concave up, so it'll be negative derivative values, but with a positive slope. So something like this. And then prior to that, we have a decreasing graph, so still negative derivative values down here, concave down, so it's going to have a negative slope because the second derivative is negative there. What did we just make? That looks a lot like the original graph of f of x, especially if I get rid of all these lines. Right? So what did we just find? That's a very striking result, and this is so important to calculus. What we just found out is that if you're doing an accumulation function on a little f here, so you're doing an accumulation function on this guy, the actual accumulation function, we really don't worry a lot about that. But the striking thing is that the derivative of the accumulation function is the function itself that you are integrating. So our hypothesis that we're going to try to prove is that the derivative is actually the small function that we were integrating. And we see that by the picture. It sure looks a heck of a lot like that's true. So let's see if we can prove that somehow with a picture. So I'm actually not going to use 0 this time. I'm just going to say, let's say we start at some a value. Okay, so let's say we start at some a value right here. And what we're going to do is we're going to integrate up until we get to x. Let's say x is right here. So if we're going to integrate, I'm going to use our vertical lines again because we've been using rectangles to integrate. Many rectangles, right? An infinite number, right? So what we're saying here is our capital F of x is equal to the integral from a to x of f of t dt. So this is my little f function, f of x. And we're using t because we can't use x because we're using that elsewhere in the function. So what we're saying here is that the amount that capital F, the accumulation function, is changing, we want to actually try to show that the derivative, so is capital F prime of x equal to little f of x. And kind of just looking at the picture, that makes a lot of sense to me, because think about how much you're changing at this moment. So if we go just a little bit further, and there's a letter we use for that a lot. Let's say that that value right there is x plus h. And we want to think about that area right there. Because if h is very small, that area is really how the graph is changing at that moment. So what that would mean is the amount that the accumulation function is changing. So delta capital F of x would be equal to the height of this bar, which is little f of x, right? That's the height of that bar, because the height is approximately this guy right here, and then multiplied by some change in x. And that would be the distance between x and x plus h. So you could say that's h, but I'll just use a delta x. So this is kind of the first hint, is if you divide both sides by delta x, you have delta f divided by delta x, which is a difference quotient, right? This is a change in the function divided by the change in x, that's like a derivative, is equal to f of x. So again, it makes sense to me that if you're making this infinitely small, that difference between x and x plus h, really all you're doing is adding a line. Let's see if I can change color here to emphasize that. You just have a line right here, and the height of that is f of x. So the amount that the area is changing at that moment is f of x. And this works anywhere. If x is right here, here's our x plus h. That area there has a height right here of f of x. Any point you're at, it doesn't matter where you started. We could have started here, or here, or here, or over here somewhere. It doesn't matter what the function looks like. All that matters is how it's changing at this moment and how high that function is. So this derivative is actually equal to the function that you are integrating. That's crazy. And it kind of makes sense, especially when I think about this point, because if this is the derivative, right? If this guy right here is the derivative of the accumulation function, that means that right here it changes positive to negative, which means that that should be a maximum of the accumulation function. Well, let's think about it. This entire time you've been adding positive area, and then all of a sudden you start taking area away. So yeah, you're going to have an increasing function up until that point, and then at that point you're going to hit a maximum because you're going to start taking area away. So it makes sense to me that this function, this little f of x, is going to be the derivative of the accumulation function. That's just weird. That means you're looking at the derivative every time that you have any function you're accumulating on. That's pretty crazy. So let's see if we can get a little bit more mathy proof. So I'm going to draw that graph again. So we have something like this. Okay. So here's our a value that we're starting to integrate from. And here's our x value. And then here is our x plus h. Okay, so we're integrating up until x, and then to x plus h, so this little area right here. So let's just use our limit definition of derivatives. So if capital F of x is integral from a to x, f of t dt, then we know that f prime of x, and this is just definition of derivative, it's the limit as h goes to 0 of capital F of x plus h minus capital F of x divided by h. That's just limit definition of derivative. So let's actually plug these pieces in. So that's the limit as h approaches 0 of integral from a to x plus h, f of t dt, minus the integral from a to x of f of t dt, all divided by h. Well, let's think about these areas. Use some magic technology with colors here. So the integral from a to x plus h, that is everything all the way up to x plus h. Okay? And the integral from a to x, that is just the area up until x. So we stop right there. So if we take the red area and subtract the green area, what are we left with? Just this area right here. So it's the area underneath the curve of little f of x that is between x and x plus h. So really this is just, we're using one of our integral properties. The top of this fraction is just the integral from x to x plus h. That's the only part of the area that's going to be left, because we're taking all the way to x plus h, and then we're subtracting off the part that goes to x. So this is the limit as h approaches 0 of the integral from x to x plus h, f of t dt, divided by h. So let's zoom in on that part. So if we just have the rectangle, and this is actually a curve, so here's our x plus h. We learned about this value in 5.3. So actually, this value, the integral from x to x plus h divided by h is the distance between x and x plus h. This is the average value of the function between x and x plus h. So we learned that that has to be between the minimum and the maximum on that interval. So it's going to be somewhere in there. This is the average value on x to x plus h. Okay, so that is our average value from x to x plus h, and h is turning into 0. So h is turning into 0, which means this value is going to get closer and closer in here. The closer that that value comes in, the more that these two are going to be closer together, these two vertical values. So as x plus h is closer to x, the average value is going to be approaching f of x. So this limit is equal to little f of x. So we've just shown by limit definition that the derivative of the accumulation function is indeed equal to the function that you are integrating. That's crazy. So really all you do is, if you have f of x equal to this accumulation function, if you want the derivative, you just dump the x into the function value right there where the t is. That's weird. So let's actually see what this fundamental theorem of calculus is. So if little f of x is a continuous function, sorry, my handwriting on here isn't great. So if little f of x is a continuous function, and we define capital F of x to be equal to the integral from any a value. You can start wherever you want. We saw that in our picture. Doesn't matter where you start, because really all that matters is what happens where you end. So integral from a to x of little f of t dt, then capital F prime of x is equal to little f of x. Okay? So the way that you often see this written is that the derivative d dx of the integral from a to x of f of t dt is equal to f of x. And the reason they like to do this is because then you don't have to bother with this capital F lowercase f thing. So if you want the derivative of an accumulation function, it's equal to the function that you are accumulating on. Pretty cool.
Okay, well, that was a lot of theory. Make sure you check out the next video. There's going to be some applications and examples for how we can use this theorem, but I wanted to make sure there's a break in between because I think that's a lot to digest. So I'll see you in the next video.